Thank you. Yeah, I'm very excited to be here. It's my first visit to the Institute in Princeton. So today I'd like to take you on a little tour about what we have been doing in the world of time domain astronomy, and especially trying to tell you where is the frontier that we are trying to sample with observations. So we start with a little bit of context. That's always good. And here I try to put together a slide with the main reasons why we study transients. And we start from cosmology. We all know type 1As are good distance ladders. But even if we don't care about cosmology, we know that transients release in their environments the chemicals that they synthesize during their life. So they play a role in the chemical enrichment of their environments. And while doing that, they also release in the environment their kinetic energy. And they do play a role in galaxy evolution as well. And here we see these beautiful outflows. Of course, we are all familiar now with gravitational waves produced by black holes and neutron stars that are emerging. And one easy way that the universe has to produce these compact objects is through stellar explosions. So for all of this reason, it's a good idea. This, for me, is a good motivation to go and try to understand what these transients are. So here's the story and the type of questions that I try to attack with my team. So we start with our massive star, and in most cases, we do not know which type of star produces which type of explosion. So we do know stellar progenitors only in a few rare cases. But for the majority of our cases, we do know that they explode, but we are not yet at the point observationally to link this type of star with this type of stellar explosion. But also on the other side, we are not doing particularly better in the sense that we do know that stars explode. We do know that they form neutron stars and most likely black holes as well. But what each supernova produces, so which type of compact object this supernova produces, is not known. And it's not even known for our closest supernova during our lifetime. So we do know, though, that sometimes massive stars, actually most of the times, they hang out in binaries or intervals. And if we start out our system with good conditions, it's possible that both stars will manage to stay together all the way to the end. And maybe they form compact objects that later merge and produce these beautiful gravitational waves that we can now sample with our detectors. And here the question is, OK, with LIGO is telling us of the properties of the things that are emerging, but what is left behind there? What is the object created by these mergers? So in terms of questions, here are the main questions that I try to attack. So how do we get to the end? What happens in the last thousands of years before stellar death? There's a huge, big question mark in stellar evolution. So how these stars explode, and I know that here you have somebody that's trying to explode stars in the computer, and my approach is different. I'll try to use observations to constrain the explosion mechanism instead. And what are the properties of these newly born black holes and neutron stars? What are their masses? What are their spins? And what is the EM, electromagnetic signature, of these mergers? So these are the questions that shape my investigation. So why now? We have been having these questions for a long time. So why now is a good time as an observer to go in, to jump in, and try to find a solution, find an answer. And I'm going to give you two arguments. And the first is effectively a technological improvement. So we are now very lucky to live in this era where we can sample time. We can sample the fourth dimension. We can literally say, OK, this thing appeared in the sky tonight, and it wasn't there last night. This is something that is happening in the optical. It started out in the optical. And I put here some of the major players. Well, I was at Harvard. I was connected to Pansters. But I wanted to be fair. I put here the picture of our enemies, too. I'm kidding. But and then I put here the future. This is LSST. I'm involved with I'm chairing the gravitational wave follow-up team, a subgroup within LSST. And I truly believe that this is our future here. The good news is that this revolution that started out in the optical is now slowly encompassing the whole spectrum. And the radio sky is the one that we'll see very soon, actually, is already happening. This revolution, this capability to say, hey, there is a new radio transient I didn't have. To be fair, the UV and the X-ray sky, the soft X-ray sky, are the two ones that are sort of lagging behind. What we would really need, it would be a wide field UV, wide field soft X-ray capability in space. So what have we been doing? We have these new tools. What have we been doing? So the first thing is there are transients that we knew that were there, supernovae. But since we can do a much better job, we were able to sample new pieces of the primary space of these transients. So for a long time, in the supernova field, we were relying on amateur astronomers. And you might be surprised that even now, with all of these machines, amateurs are still doing a crazy good job in the local universe. And you know, amateurs are amazing, but they are humans, and they tend to find things when they are luminous. That meant that we were losing a little piece on the evolution of this supernovae. And it turns out that a lot of information is encoded in this rise time, information about what type of star is exploding. Another thing that came as a surprise is this pre-supernova outbursts. So when I was a grad student, I was taught the stars would sit there quietly, waiting for death to arrive. And nothing would happen in the last thousands of years before stellar death. And we could find evidence, real data that told us that no, this is not true. And in the first half of the talk, I'm going to show you some evidence of this behavior and try to convince you that there's something that happens across the mass spectrum of stars. The other thing that, of course, happens every time we have new capabilities, we find new stuff that we were not thinking about. And today, I will concentrate on these very fast evolving transients, and I will just mention the superluminous supernovae. So superluminous supernovae are the most luminous of a supernovae, like 10 times, 100 times more luminous than a normal supernova. And it's very interesting that we discovered this, we came to understand the existence of the most luminous types of supernovae in 2012. And one might wonder, why were we missing on the most luminous types? I would guess it would be easier to lose the faint ones. But here's the reason. So the first part of the answer has to do with timescales. So we were used to sample the sky, let's say, every 15 days or so, something like that. And superluminous supernovae, they just have very long rise times, which means that the delta brightness between these epochs is small, which means that if you have a search that is tailored to find normal supernovae that rise much faster, you just filter them out as noise. The other piece of the story is that superluminous supernovae, they bridge observing seasons. So in the optical, there is a sun, and sometimes you can observe. And it just happens that superluminous supernovae, they start in one season, they end in another one. It might seem very, very stupid, but it's true that as observers, we tend to concentrate on what happens in one season, and we forget about what happened before. And that's why they were not found. Fast transients is instead a completely new class. And here is very easy to understand why we were missing those. We were just not sampling the night sky fast enough. So timescales is the first reason. Second reason, and we are now going from something like this to something like that. So we can really see what's new every night. And the other piece of information here is that we evolved out from targeted searches. So amateur astronomers were pointing at galaxies, and usually they like big pictures, as everybody, and they tend to point at this type of galaxies. But it just turns out that there are classes of transients that do not necessarily like these big spirals. And this other galaxy might not look as handsome as this one, but it's a very, very interesting place to look for transients. So basically, by sampling the sky more and more frequently, and by having an unbiased way of searching for transients, we are now finding new stuff. Those are the two ingredients. And this is optical. The second point that I want to make is that, as I told you, this technological revolution is slowly encompassing the whole sky. And we can do a truly multi-wavelength follow-up of transients right now. And the way I see it is just as a first step towards what is now reality with this multi-messenger endeavors with neutrinos and gravitational waves together with photons. So the way I tend to look at this is that this first point is giving us discovery power. So we have these surveys that are our discovery engine. They tell us where to look for interesting stuff. And then with multi-wavelength, truly multi-wavelength follow-up from gamma rays all the way to the radio, we can understand the physics of what is going on. So discovery plus understanding to make progress. So these are the questions that I'm trying to attack using these new tools in the sky. And the way we do it is the following. So I'm a strong supporter of multi-wavelength studies. And when we have something of interest in the sky, what we do is that we go ahead and trigger. This is literally what we triggered for this transient 18 COW. This is just to say that we truly span the whole spectrum. And as you might guess, there is some social skill that is needed to interrupt all of these people and say, hey, stop, it's my turn, repoint to where I want. If you're interested to know that part too, please ask me. So truly multi-wavelength studies. So if you want to do that, you also need a team that has a broad set of expertise. So I am very lucky to work with all of these young minds at Northwestern. And each of them has one wavelength where they are true experts, but they also understand how observations are acquired across the spectrum. And together, we do some modeling. This is a latest addition to my team and my machine learning effort that is our discovery engine. So we use machine learning algorithms to find interesting things out of the thousands of alerts that come in every night. And this is if you want to know who is what in terms of level. OK, so let me first concentrate on this first half of the problem. So what happens in the last thousands of years of a star that is about to go through core collapse? From an observational perspective, if we want to learn about this last thousands of years, we have three methods that we use. The first is the simplest you can think about, direct observations. So we have these maps, we have these images, we just go back and see if there are outbursts there. This is a place where I believe LSSC is going to really blow up everything out of the water. So LSSC is going to go very deep, and we'll have at the end these 10 years a baseline that will allow us just to say, OK, here is a supernova. Tell me what happened before in the last 10 years. And it's going to tell us timescales, luminosities of these outbursts in an unprecedented detail. And here is what I still consider one of the best examples, and the one that really sent a wake-up call to the community. The Supernova 2009 IP, the name could be no more misleading than that, was called like that in 2009 because we thought it was about that the star exploded. In reality, the star, that's 2009, somewhere like here, then underwent a number of outbursts, and then we had a way bigger outburst, which we believe is the true supernova explosion years afterwards. So bottom line, since we had this very detailed view of this outburst, it was clearly telling us, hey, the star is still alive. So even if we were not expecting outbursts just before stellar death, well, nature does it.
Which telescope are these data from?
Those are actually amateurs.
So the time sampling is whatever they happen to have.
Correct, yeah, yeah.
It looks like if you had even finer time sampling, it would be even more interesting.
Exactly, and if you do the temporal analysis of this outburst here, and there is some data that I'm not plotting in this plot, there is a recurrent time scale that emerges that is around 40 days. It's not periodicity, but it seems that the system prefers. There is more variance associated to that time scale. So one of the things that we want to understand is this type of preferred time scale something that happens in other events or not? Try to then extract the physics of the thing. And then on 9IP, as I said, it was like a wake-up call to the community. Say, hey, there is something that probably we don't understand, and we need to put more effort to see if that is common or not. And then more and more examples were found where you can see that a supernovae not all the supernovae have these smooth light curves that we are used to, but they do have outbursts, and some of them are as close in time to the main outburst as 40 days before. So after that, we understood, OK, we need to pay attention to what happens before. And we did numbers. And for 50% of the supernovae, for which we had deep enough photometry to see something like that, we could see evidence for some outbursts. Quick question? No. So this one will be type 2N. Type 2N, I find it as a classification is very misleading. It just tells you that you are interacting with hydrogen. But you can be anything in the core. Yeah. So one thing that happened with the 9IP was that we were very lucky. And in 1999, HST was pointing at that part of the sky. So on one hand, we were very lucky. We could pinpoint at this star that was doing this type of behavior. And if you do some numbers, given how bright is this dot, it will tell you that the star needs to be massive. Now, the 60 versus 50 depends on which evolutionary track you use and how you correct for the colors that we don't have in this image. But the message is, it's a massive star. So that was good and bad, because the community, the reaction was, well, you know what? These stars are not even 1% of the IMF. So at the end of the day, why we should care about something that maybe just happens at the end of the mass spectrum of stars. And in the remaining part of this talk, I will try to convince you with data that this is not true, that these outbursts are there, and they span the whole spectrum of stars, including the vanilla type stars that are giving us the normal core collapse supernovae. So this is the way I like to think about where our discovery spaces and where to try to put all our resources. And the pre-supernova outbursts, I truly believe, will be big discovery space, and especially when LSST is going to be up and working. The other tool that we use to learn about what happens just before death is flash spectroscopy. Here, it's very simple. We have an explosion. This doesn't happen in a vacuum, and it does illuminate material that was left there by the progenitor just before death. And by getting on target, and I want you to see how early, the 6 hours after explosion, if you're technically good enough to do that, then we can learn about the composition of this layer that was very close to the star. So most likely, this is telling us the composition of the star just before stellar death. That is something that Avishai Gallium pioneered as a technique. The third way that is very close to my heart is using the shock as a way, the supernova shock, as a way to learn about the past of the star. So as before, supernovae do not happen in vacuum. They launch a shock through the environment. The shock accelerates particles. And this is a very well-known source of non-thermal and thermal radiation, synchrotron Bremsstrahlung. So by mapping this radio and X-ray emission with time, what we try to do is to understand how many electrons have been accelerated equal how much stuff has been piled up, has been swept up by my shock, and then reconstruct the mass loss history of this star before stellar death. So the reason why I like this method is very simple. The velocity of the shock is much larger than the velocity of the ejection before stellar death, which means that at any time t of my monitoring, I'm looking back in time what the star was doing of a fraction, this V shock, V ejection, and this can be easily all the way to 1,000. So if I'm good and I do a follow-up of this supernova in the X-ray and radio for 1 year, a few years, I can learn how the star polluted the direct environment in the thousands of years before stellar death. Yeah. Say it again? Yes. Yeah. So the reverse shock will be a huge component in the X-rays, especially in the X-rays. Yes, 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 yes. Which actually makes it good and bad because you have two shocks that are producing radiation in your band, which makes it challenging sometimes to understand what is what. Yeah, excellent question. So while doing this exercise, by doing monitoring of supernovae across the spectrum and sampling their environment, we started understanding that there are some trends. And here is a plot to summarize where we are right now. We have the velocity of your fastest ejecta, so the fastest ejecta produced by the explosion versus the density of the environment here at a particular radius. And the level of stripping of the star grows in this direction. So type 2Bs is when we still have some hydrogen around. And here are those stars that don't have any signature of a hydrogen in their spectra. And what you can see is that we start to see a link between the structure of the star at the time of a core collapse and how much stuff the star lost to their environments. So that's the first link between where stellar evolution takes you and how you explode. But of course, while doing this sort of exercise, we ran into surprises. And one of the most beautiful ones is what we found for this supernova, 2014C. So the most beautiful piece is actually this image. And for an X-ray astronomer, this is heaven. Here you're looking at the first image of an extragalactic supernova in the hard X-rays. And I do remember when I was trying to get NuSTAR to repoint to this object, and I called up Fiona, the PI of NuSTAR. And I was like, hey, Fiona, can you give me 20 kiloseconds, which is like peanuts, to repoint this supernova? And she said, Raf, look, NuSTAR is not done to repoint extragalactic supernovae. You'll never see anything. But I was persistent. And at the end, she said, OK, whatever. I'm going to give you 20 kiloseconds, and then we're good. And here you go. This is the first image. This is a very bright source. And I can tell you that 5 years afterwards, the supernova is still bright and still detectable by NuSTAR. So, and after that, we have been repointing regularly supernovae with NuSTAR.
What's the extended life around the source?
That's a PSF. So NuSTAR has a 1 arc minute. PSF, yeah. So for an X-ray astronomer or anybody that has worked with Chandra or XMM, this is extremely useful for this simple reason. So we were used to just get 1/2 of the SCD. This is where Chandra or XMM give you. So we were always left with just one side. With NuSTAR, for the first time, we could see the whole thing. So we could really constrain the temperature of the emitting region in fine detail, and also the level of absorption. That is what makes partially makes this thing curving down. And that is extremely beautiful because temperature speaks to the velocity of the shock, and so it gives me the opportunity to reconstruct the dynamics of this shock. So why 14C was such a bright source of hard X-rays then? So I think that we all grew up with this idea, at least I did, that supernovae are either type 1 or type 2. So hydrogen poor, hydrogen rich, and that's it. And 14C is the first object for which we could witness in fine detail a complete metamorphosis from type 1, like the most normal type 1 supernova, to a type 2 supernova. So to the point that when I go around the supernova conferences and I show the spectra, and I show one spectra from this phase and one spectra 1 year afterwards, they tell me, oh, this is a type 1, this is a type 2. And then I show what happened in between and say, wow, it's the same thing. And here is what happened. So start from the optical, then I'll go into the radio, and then we will go into the X-rays, and I'll put everything together to see what is the physics that is causing this metamorphosis. So 14C happened in this galaxy, a remarkable galaxy, but it's 60 megaparsecs. And to anybody that does follow-up in radio or X-rays of transients, this means, OK, close enough for you to have some chance to see something. As a rule of thumb, beyond 50 megaparsecs, supernovae are very dim in X-ray or radio, so you need to have a special supernova to give you some detectable radiation. And here is how it developed in the optical. I don't care about the details. All I wanted to take away from this plot is that it's in the middle. So it's completely unremarkable in terms of optical luminosity, just in the middle of supernovae. And if you take a spectrum, this is also very, very normal. So you see 14C in black, and then you have a 1B supernova, OAD. And you can see that the two spectra are almost the same. This is a very unremarkable type 1B supernova. So no hydrogen, yes helium. So the bottom line is that at early times, this is very normal. Nothing stands out. However, the way we do follow-up of supernovae is that we try not to neglect them and forget about them after 100 days, but instead, we keep looking to see if something happens. And here is what happened. You have arrow of time going in this direction, and you can clearly see something that happens, and zooming into the H alpha line here. So you have some emission from the host. This is the host H alpha. And then we start building up this broad hydrogen line profile, so which is the one that causes, with time, a transition from a normal type 1b supernova to something that looks way more like a type 2n supernova. If you look at this supernova in the radio, and here I'm plotting the whole world of radio supernovae, so luminosity versus time. And here is how 14C behaves. So it starts out in a very remarkable place, but then it goes up. And I can tell you that right now, we are still here. We're still here. We're still going strong. So differently from all the other supernovae, or most of the other supernovae, this one has a rising radio emission with time. Now, let's go into the X-rays. And if you thought that, well, in the optical, we have right now something like 44,000 supernovae that we know. In the radio is more like 80 supernovae that we have reported. And here is the world of X-rays. So you understand why I do believe that we are missing out a little piece of information here. So when we say light curves in the X-rays for supernova, it means 2 data points, most cases, yeah. So here is where 14C started out. And then just like the radio, the X-rays start to go up, and we are still here. So we have an increasing X-ray luminosity with time. Not only is increasing, but the spectrum, the X-ray spectrum in the soft energy band is very hard, because the temperature is a Bremsstrahlung spectrum with a temperature above this 10 keV. So let's put everything together. So we have this supernova that is going from type 1 to type 2. And then we have increasing radio, increasing X-ray. So here is what is going on. I'm sure you already know by now. So the picture that we went in is that around our star, we were expecting this wind-like medium, hydrogen-free. Instead, what happened is that the shock from this supernova slammed into an overdensity of material that was enriched in hydrogen. And we can constrain the location of this material pretty nicely because we have the multi-wavelength follow-up. So synchrotron is basically telling me where is the radius of a shock. And this distance is very interesting because it's very close to the dying star, which means that if this material comes from the star that just exploded, well, this must have been ejected not too long ago. I don't have a good handle on the velocity of the ejection, but with some assumptions, like this is a 100 kilometer per 1,000 kilometers per second to 20 years, we can say that this ejection must have happened around 20 to 1,000 to 2,000 years just before stellar death. So now we can describe the medium that we see thanks to the observations. But the most interesting of the questions is why? So why we have this shell of hydrogen-rich material sitting so close to a completely hydrogen-poor star? And we thought about 2 possibilities. And the first possibility is that this hydrogen envelope was lost because of some sort of instability that are intrinsic to the last phases of the nuclear burning sequence. So here, I don't want to be specific. What we need is something that is tied to the nuclear to the evolution of the star that is dying. And what I need is a process that deposits at the base of the envelope some energy. If this is true, then the prediction is that this is tied to the evolution of the star that is dying. So this mechanism knows that the end is approaching. So while for 14C, based on n equal 1 statistics, I can't tell you if this is true or not, this mechanism has a strong prediction that if I do monitoring, well-done monitoring of other stars, I should see these ejections to happen roughly at the same time. The other possibility is instead binary evolution is the binary evolution. So this the progenitor is not alone. There is a companion. And the companion is helping out with unbinding the envelope. In this other case, there is not the companion, to some extent, doesn't know that the end is coming from the other star. So if this is true, what I should observe, I should observe in other stars would be a sort of a homogeneous distribution, more homogeneous distributions of these shell ejections with time. So again, based on this n equal 1 supernova, we could not understand which of the two possibilities is right. But this is why we embarked on a systematic search for these shells, for these ejections in a bunch of supernovae. And before embarking in a search, if you want to convince VLA to give you tons of time, you have to show that you did your homework. So we went through the VLA archive. We used all of the VLA observations of hydrogen-strip supernovae, and we looked for other supernovae that shows this late-time radio rebrightening. And we could find 4 out of 44 cases for which we had good data, data that are deep enough to see these kind of ejections. So we can say that based on that sample that is in no way complete, no way homogeneous, no way controlled, 10% of stars are doing that on this time scale. However, because the monitoring of this supernovae was not strategically planned to look for this kind of ejections, we have these bars that are quantifying our ignorance at any time t after the explosion about which of the systems are interacting or not. Equal, is there a shell or not? So the goal of my research with my team is now to shrink these bars, reduce their size, and tell you, yes, we have evidence for ejections at this time in this amount of stars. And then use this as information then to try to understand the physics of whatever mechanism is behind. So this is to summarize our way to learn about what happens in the last moments of life of the stars, direct imaging, and then radio and X-ray observations. And and flash spectroscopy. I want to emphasize that the only way that we have observation right now to learn about extragalactic stellar explosions and stars in this phase of evolution is using the shock as a probe of the environment. So other questions about this first half of the talk? Because I'm going to transition into, yes, Michael.
So
and then.
is a star that I imagine might be, when one thinks of shells and stuff.
Yeah.
Can you put that in this context?
Yeah, Eta Car in 1820 had the great eruptions. So in that case, the amount of mass that was ejected is indeed comparable to this, or even larger. But the time scale is much longer. It's 20 years. So my suspicion is that what we're dealing with is not one single mechanism that gives us the whole thing, but there must be different mechanisms that are leading to these mass ejections. And what led to the Eta Car eruptions, I'm not sure that is exactly what we are looking at here. But great point. Yep. You had a question. Oh, okay. Eta Car. Good, good, good. Yeah, Eta Car is like the first thing that we have in our mind. It's there, and it ejected so much stuff. Yeah.
Do you have any information on color, any constraints on the color of the star?
For in this case, we only had Subaru observations. So what we could do is just to study the stellar population that was leading to that. And we have an evidence that probably the most massive star allowed by the IMF that we can constrain is around 13 solar masses, which might suggest that the binaries might have a good reasonable role in this phenomenology. Yeah. Yeah.
In the binary scenario that you mentioned, what does the explosion do to the binary?
Mm. It's not the explosion, it's just that the binary would just help you binding the envelope. The envelope is star. So if this is a massive star, the envelope is not so terribly gravitationally bound to the star. And it turns out you need just a little amount of energy to explode it, and you can steal it from the companion. Yeah. So hopefully I will last to the end. I am a little bit under the weather. So let's now concentrate on this other side of the problem. This is one of the questions that I find the most interesting right now. So which star produces what? What are the properties of these black hole and neutron stars? And I've been thinking a lot about how to solve this, how to get some hints from observations. And I'm talking specifically here observations of young supernovae, not the ones. Of course, we can use the remnants in our own galaxy to sort of understand something about it. But I want to, in my dreams, I would like to say, okay, this type of stellar explosion, this type of star leads to this type of stellar explosion, and this will give you this black hole or neutron star. That's the dream. So we do know, of course, that this is one way the universe produces compact objects. As an observer, I tend to believe two things when I see them. And yeah, we know the Crab Nebula has this beautiful neutron star sitting down there. So 1,000 years afterwards, we can see it. And of course, this is not the case when you have a young supernova. In that case, even if a compact object is formed, that sits deep down, few solar masses of ejecta, and no matter what this compact object is doing, we are not seeing it. And what we have to do is to wait. So one approach that I'm using right now is to go back to supernovae that are a few years old or more, and see if the ejecta has diluted enough for me to see some evidence for a light bulb that is shining, like a surviving magnetar or something alike. So what we look for specifically is signatures in our spectra of high ionization. So it's something that tells you, okay, you have a light bulb that is ionizing your ejecta. So what you're looking for. So this is something that in the era of the ELTs is going to be extremely powerful as a technique. So go back and see if there is something that shines through it. But again, you need to wait for years because you need the ejecta to become transparent. So if you're not patient, and I'm not, then I was thinking, what can I do to try and see if there is a compact object formed? And it turns out that part of the answer might be here in this very fast evolving transients. And if instead of starting from something like that, we start out with something that has way less ejecta to start with. So a supernova that just produces little tiny amount of ejecta. So not solar masses, but let's say point something solar masses of ejecta. And if this ejecta, instead of being spherically symmetric, is asymmetric, that would give me the best possible conditions to have this possibility to see radiation coming directly from the central engine. I'm going to call this thing a central engine. In this case, I would have some paths where this radiation might be able to escape if it is there. And as I said, this is something that I believe is very much related to the phenomenology of this completely new class of transients. It's so new that we don't even agree on how to call them. So we call, most of us call them fast and blue optical transients, which is like just a description of what they look like. But some other people, when the color is not known, because if you don't know it's blue, then it's a felt. It's a fast evolving optical transient. But what we mean is something that gets to peak. Here's what we mean. Something that gets to the peak luminosity in a few days. And here, there is no rule that decides the extent of this bar. It's just completely made up. But here is where type 1As are with beautiful relationship that allows to do cosmology. this is where superluminous supernovae are. And I want you to, right away, to take home this message. Look at these F-bots. They can compete luminosity with the most luminous supernovae ever seen. They can get above 10 to the 44 erg per second, extremely luminous. And yes?
The x-axis is a time from explosion to peak luminosity?
It's a, yeah, so different people would define this time scale in a different way, but yes, you can think about that as a rise time. Yeah. But what I want to say is that these F-bots not only rise fast, but they tend also to decay fast. Yeah. So you can see that they span a wide range of luminosity, and that to me tells me right away that most likely we're not dealing with a homogeneous class. It's very much possible that what happens to these guys at the very high end of the luminosity above superluminous supernovae might not be what we see, what causes these other ones. But right now we are at the point where we can only call all of them F-bots. And just like every other time that we don't know what we're dealing with, one way we try to understand things is by looking where these transients are born. So we try to learn about what transients are based on their locations. And here I can tell you that all the published F-bots are in star-forming, associated to star-forming regions. So they are not linked, they are not related to, there is no evidence for them to be related to a null stellar population. Okay, so we have fast time scales, and we need to be fast and we need to be luminous. These two ingredients tell us right away that the typical normal supernova that is powered by nickel-56 is ruled out. Very, very simple argument. To power luminosities all the way to 10 to the 44 erg per second, I would need several solar masses of nickel. By the time I put there that amount of nickel, the diffusion timescale becomes so large that it would never go up to peak in a few days. So this simple argument tells you that if we want to power first of all, that the normal supernova mechanism is ruled out to power the luminosity, but also that if we want to power this transient with a source of energy that sits inside the ejecta, well, for the very same argument on the diffusion timescale, the ejecta around the F-bot can only be tiny, right? So bottom line, I am solving the problem of the energy by adding an extra energy term in my equations. And here, I'm putting it deep down, sitting in the center. And here, the requirement is that just a little amount of ejecta around me. The other possibility that I have is that, OK, I don't put this extra energy term deep down, but I put it outside. And here, what we're thinking about is like shock interaction. That gives me this beautiful opportunity to convert very efficiently kinetic energy into radiation. So in this case, the very, very fast rise time scale tells us a lot about the properties of this shell with which I am interacting right now. There are two predictions about this model. So the first is that, OK, I have a shock that slams into something, and then the shock goes through the shell. After that, the shell will cool down. So if this is the mechanism, what I would expect to observe in these F-bots is a cooling, progressive cooling of my ejecta with time. The other thing is that depending on how large this radius is, this will wash out fast variability timescales on my signal. So if this is the scenario that I'm dealing with, I want cooling, and I don't want things to vary too fast. Until now, until 1 year ago, there was no information about F-bots outside the optical. And one of the missions of my team is to try to find evidence of transients across the spectrum. And I can tell you that, yes, we managed to see actually 2 F-bots in X-rays and radio. And one is published, and the other one just asked me about it if you're interested. It's going to be out in a while. So here is the frontier for F-bots. And we need to talk about cows. And the reason is that this poor transient happened to be named COW. and this is how it soon became the cow. So if you go to a transient conference and people ask you, how is the cow doing? That's what they mean. Yeah, it's kind of interesting. And the press also asked me, what did we learn about cows? So we learned nothing about cows. We learned, yes, very interesting. So here's, and this was the transient for which we activated all of our programs that we had in place. It's at 60 megaparsecs, and you might think that it's far away, but F-bots are rare, intrinsically rare in the universe. And before the cow, the closest was at 500 megaparsecs. So having something at 60 megaparsecs directly bought us like a factor 100 in flux that we could see. So it was the best possible opportunity for us to get on target. That's why we started all of that follow-up. And here is how it looks like. I'm plotting in R-band mags, and you can see how fast it goes up. And you might think, well, it goes up to the level of a normal supernova, but it doesn't touch superluminous supernovae. But it turns out that the cow is so hot that the volumetric correction that you need to apply to the R-band is so large that after doing that, it does compete with the most luminous of the supernovae. So it's something that went to peak in 2 days and went all the way about 10 to the 44 erg per second.
Based on UV observations?
Correct. Yeah. Swift UVOT. Yeah. And actually, the first thought was that it was a CV in our galaxy before getting the redshift. That was the thing I would have bet my salary on. But no, it's a 60 megaparsec, so we have to deal with it. So here is how it looked like. So at the beginning, as a spectrum, it starts out as featureless. It's blue and featureless, which is telling us right away that the features are very broad, and that's why they're all blended. We don't see anything. And then with time, we cool down, and we start producing lines. And very important, we see hydrogen. It's very, very important, because one of the things that came to our mind was, well, what if we have a neutron star merger with some properties that we don't understand? But no, we have hydrogen, we have helium, so most likely no. The other thing that is very important is that, look at the temperature. We start at 30,000. It's very hot for supernova, 30,000 Kelvin. And we start going down, fine, but at some point, we stop. And we stop at 50,000. This is where usually supernovas start off. So this transient never cooled down more than 50,000 Kelvin. So this gave us the idea that, well, something is keeping this ejecta hot. Very different from a normal supernova and anything connected to a stellar transient, the stellar explosion that we've seen so far. Not cooling. The other piece of information, the other beauty of the cow is the following. So we started X-ray follow-up, and here just concentrate for a second on the black dots. And look at this beautiful variability. This is true intrinsic variability of the transient. It's not instrumental effect. And you can see that, the flux goes up and down. At the beginning, the X-ray flux goes down like t to the minus 1, which is sort of normal for an expanding blast wave. And then, on top of the variability, it also shuts off very, very quickly. So this type of flaring activity is something that we have only seen in gamma ray bursts or tidal disruption events. Those are the only two cases. Never seen here. And again, this very short time scale of variability is not consistent with the idea of having a shock with a large radius that is plowing through the environment and then producing this variability. And here's, if we put the cow into the context of X-rays from stellar explosions. And a lot of us, a lot of the people in the community thought that since the cow was so luminous in the X-rays, they thought that the cow was a gamma ray burst. So the only supernovae that we know of that produce 10 to the 43 erg per second in the X-rays are gamma ray bursts. So the first thought was, okay, it does have flaring, it has this luminosity, it's a gamma ray burst with hydrogen. But this is not true, and we know it's not true. Why? Because we did the radio follow-up. So here is how supernovae look like in the radio. Usually they are synchrotron self-absorbed, synchrotron emission, and then they cascade down as the shock propagates. And by monitoring the evolution of the peak flux and peak frequency, we understand we can constrain radii, and we can understand how thick is the environment this blast wave is going through. So by doing this super traditional exercise, what comes out is the following: that the cow, putting the peak versus new peak and time peak, this is the three things that you can measure from radio. The cow sits on the V equal 0.1 C line. So the shock that is powering the radio emission in the cow is not a gamma ray burst shock. It's not a V equals C shock. It's 0.1. That's very normal in supernovae, very different from gamma ray bursts. So what we're looking at is not a gamma ray burst. 98 BW, where is the question coming from? Oh, here. It was a 0.4, 0.5 C. It's yeah, it's a mildly relativistic shock, 98 BW. So, but the other difference with 98 BW is coming up right now. So not only the shock is lower, but also the environment is crazy dense. So here A star is 10 to the minus 5 solar masses per year, and a typical volt per year, and the environment of the cow is at least 10 times, 100 times denser than that. And here I'm doing things in equipartition, so this is a lower limit, effectively, to the density. So the environment around the cow is not GRB-like. The velocity of the shock is not GRB-like. So we are dealing with something that is effectively different.
What density are we talking about here?
Is the density of the environment that is sampled by
How dense?
it's like 10 to the minus 4 solar masses per year, equivalent to 1,000 kilometers per second. Yes, yes, yes. A star is for 1,000 kilometers per second. Thank you. Yes. So, and the other thing that we can constrain is how much energy is carried by the blast wave. Again, it's an equipartition argument. So this is a lower limit to what is carrying. So it's a healthy blast wave going through an environment.
What is the photo exposure energy?
They radiate, yeah. So they radiated energy. Consider it was 10 to the 44 Earth per second. It lasted a few days. So and then you put some correction for kinetic into radiation, let's say 10 to the 50. So, and here is how the cow compares in the world of radio and radioluminosity versus time. And you have a normal supernovae in black, and you can see that it goes up all the way to being the brighter, the most luminous among the supernovae, and it does touch the world of supernovae. And your 98 BW is this one here. And I can tell you that right now, with our monitoring, we could see the decay, and it decayed extremely fast. So this supernova in the radio is now doing things that we have never seen before, extremely fast decay. But so when I was at Harvard, Bob Kirshner was used to tell me spectra are truth, and I say SEDs are truth. So we struggled a lot and to try to understand what each component is. And what you're seeing is something that I find not as satisfactory, in a sense that we had to invoke three components for the three pieces of the spectrum that we were monitoring. So the optical is this black body, so thermalized radiation. The radio is this shock, synchrotron emission. And there is no way we could find to put the X-rays together on the synchrotron line of the shock. So our conclusion is that the radio is powered by this external shock that is going through the medium, that the optical are reprocessed radiation, thermalized, but that the X-rays, they actually need their own source. And we think that what we're seeing are X-ray coming right from deep down. And I'm looking at the time. I'm doing a little bit not very good. I want to show you why we think that the X-rays are coming from the inside. And I'm going to show you what I found the most surprising of the features of the cow. I take a step back, and I go into Compton hump spectra that I'm sure that each of you that is working with X-ray binaries of AGNs are very familiar with, but I wasn't before seeing the cow. So in that case, people are very familiar with Compton hump spectra that gives this characteristic bump, and with their iron K alpha line. So, and that is powered by an inner source of hard X-ray radiation that interacts with reprocessing material that does the Comptonization. So this is something that was not in my mind. So when I analyzed the cow spectra and I put together the XRT with the null star and I had this bump, my first reaction was I screwed up the data reduction. And after seeing that integral, different spacecraft was finding the same thing, same flux, same everything, I said, okay, well, we have to deal with that. So the cow actually shows this very prominent bump above 10 keV, and it does show this little axis before. That is, if you think about it, if you were familiar with this already, it would be like very easy for you to tell me, yeah, I think a Compton hum spectrum might actually work for you. So, so we started thinking how we can reproduce this spectrum, and here's what we think it happened. So what we think is that we had this light bulb of high energy, hard radiation sitting deep down, and then we had some shell of reprocessing that would reprocess part of this material. This shell, differently from the X-ray binaries or AGNs, this shell is expanding with time on timescales that are very relevant for my follow-up. So while at the beginning, this shell is very efficient in doing the Comptonization, at later times, this dilutes. So I'm losing the reprocessing layer in that case, and all I'm left with is the emission from what we think is a central engine. So what we think is that the cow might actually provide, cow and cow-like stuff might actually give us this opportunity to see emission right from the compact object that is formed by this type of explosions. And this is, if you try to use your XSpec or Sherpa models for Comptonized disk refraction models of AGNs and try to model the cow, you can find a solution that is doesn't work that badly. So this is the cartoon that summarizes our views on the cow. So there is a cow in the sky. It's aspherical. We need to break spherical asymmetry to allow us to see all the different components. And it does have an engine. So we think that we had the source of a hard X-rays sitting deep down. We have a disk that is probably thicker. And we have a funnel of lighter material that allows us to see the power law from our engine directly, almost directly, together with a Comptonized direction that is, the Compton screen is actually here. So we also need to invoke very, very special viewing angle. But here's, to summarize, I do believe, and the reason why I'm so excited about FBOTs is that I believe that there might be one way to try and see these compact objects right at the time of formation and maybe learn about what they do. And this is my last slide. I hope I convinced you that even if stellar explosions are an optical phenomenon, and they put most of their energy in slow-moving material that produce the optical, there is a ton of information that we can learn by trying to collect information coming from something that is carrying way less than 1% of energy. And this is how I try to sell this picture to my students. There is value in going from optical only and opening our eyes to the entire spectrum and try to understand which physics is dominating in each side of the story. And with this, these are my questions that I'm trying to solve. And just want to tell you what is coming out soon. We have, as I told you, one of the missions in our team is to try to find X-rays and radio for all the transients. And we have now the first evidence for rising X-rays from a superluminous supernovae. We have a relativistic cow, so new of these FBOTs, that showed a shock that is way similar to 98BW. And this might be of interest for some of you. We have evidence for synchrotron from secondary electrons, so a second bump in the synchrotron spectrum. And we have some evidence for a possible pulsar wind nebula onset in the radio from a supernova that is 7 years old, and ALMA is observing for us right now. So thank you so much.